Um, yeah, sure. Yeah, so it's my pleasure to introduce Brian Harvie, who's going to be giving his exit seminar today, talking about inverse mean curvature flow, singularities, dynamical stability, and applications to minimal surfaces. So you might expect me to say this, but I do truly believe Brian has an amazing thesis that he should be really proud of. So yeah, hopefully you all enjoy what he's done over the last few years.
All right, thank you, Adam. So as he said, my name is Brian, and I'm coming off of a dissertation on inverse mean curvature flow, which is one notion of a heat equation for surfaces, and it wound up having some relationship with the mathematics of soap films. So I'll explain that later in the talk. But before I start, I actually wanted to say two things. The first thing that I wanted to say is I didn't actually have a chance to include everything that I included in the dissertation. Like there's one chapter that I'm sort of leaving out, and I'm mainly just highlighting like three big results in this talk. So if you're interested in what you see here, the full dissertation is available on the math website. And the other thing that I wanted to mention is that if you think of any questions for me after the talk that you'd still like to ask, remember that me and some other math grad students will be down at 3rd and U at 5 p.m. today, outdoors, and we'd like you to be vaccinated if you come, but otherwise everyone is welcome. So, you know, like to see you there. Okay. So since I know this audience isn't super into geometric flows, I thought it would make sense to first just kind of introduce all of the key notions and explain the significance of my results and save the proofs for the second part of the talk. So now I'm just going to just explain what a geometric flow is, what inverse mean curvature flow is, and what I proved. So in this talk, we're interested in n-dimensional surfaces in Rn+1. And the surfaces that we're considering are going to be closed, which means that they're compact and have no boundary. Think of something like a sphere or a torus that closes up, and also C2. And a geometric flow, or an extrinsic geometric flow anyway, is some sort of rule for deforming a surface like this through time by its curvature. So you imagine you have an initial closed surface and not an Rn+1, and somehow it starts moving or deforming over time with a deformation speed that depends on its curvature at each point. This is the informal picture. And we're really interested in solving for a one-parameter family of surfaces parameterized by the time variable in this case. But you can realize each of these surfaces as the image of some time-dependent immersion. So if you fix some smooth closed manifold like Sn or Tn, then you can really think of trying to solve for a one-parameter family of immersions. These are like the dimension preserving maps into Rn+1 basically, trying to solve for a one-parameter family of immersions whose images are each the flow surfaces that you're interested in. And if you take this viewpoint, the problem turns into a PDE problem. So the immersions need to satisfy nonlinear parabolic PDE as well as all the other quantities that you're going to associate with the flow surface. So you expect to see behavior similar to what you see in heat equations. Parabolic means like heat-like. Since these are nonlinear parabolic PDE, which is the twist, you can also see other crazy things happening, which we'll get into in a little bit. But before I go any further, I'm saying everything depends on extrinsic curvature. So for those of you who are unfamiliar, what is extrinsic curvature? So you have a surface in Rn+1, which has a normal vector field. And basically the curvature or the extrinsic curvature of a surface at a given point in Rn+1 gets encoded in n numbers called the principal curvatures. The principal curvatures can be realized as the eigenvalues of a tensor field over the tangent bundle of a surface. But they also have a nice geometric interpretation. If you have a surface in R3, basically the principal curvatures measure the curvature of the surface in two orthogonal directions. You know, as in like 1 over the curvature radius of this direction and 1 over the curvature radius of this direction. And they can be positive or negative depending whether or not the normal vector tilts in the direction of motion or opposite the direction of motion. And in this case, the normal vector in either direction tilts in the direction of motion, so both curvatures are positive. They can be negative. And there are two important quantities that we'll need to consider when we think about geometric flows. The first is called the mean curvature H, and the second is the total curvature. The mean curvature is the sum of the n principal curvatures of a point on the surface, and the total curvature is the square root of the sum of the squares. So I would just like to highlight that the mean curvature can be very small even when the total curvature is very large, but not vice versa, because principal curvatures can cancel one another out in the sum, but they're all, you know, positive in this expression here. So these are two quantities that will be important to keep in mind as we go forward in the talk. And inverse mean curvature flow is one notion of a geometric flow. So for any extrinsic geometric flow, the speed of the deformation in the normal direction at each point is some function of the n principal curvatures. In inverse mean curvature, the flow speed is 1 over the sum of the principal curvatures, so like 1 over h. And that's the definition of inverse mean curvature flow. You're attempting to solve for a 1-parameter family of immersions such that ddt of the immersing vector, ft, is equal to 1 over the mean curvature times the normal vector nu, okay? And this is called inverse mean curvature flow because there's a multiplicative inverse in the flow speed right here, and it's a PDE. And you can look at this from an initial value point of view. If you have an initial surface n naught, which is realized as the image of some immersion f naught, what is the corresponding solution f sub t to this equation here? And there are certain special cases where you can like explicitly determine based on what n naught is, what is nt. One of the special cases is for a sphere. So if you just have a round sphere in Rn plus 1, a standard round sphere, the corresponding solution to inverse mean curvature flow at future times is a round sphere where the radius is equal to the initial radius times e to the t over n. So this gives you a good intuition for what's happening under inverse mean curvature flow because it's telling you that this flow expands. It expands outward. Something that I should mention is that this equation only makes sense if mean curvature is strictly positive, and this normal here is the outward normal. So inverse mean curvature flow expands things outward, and in the case of the sphere, it will expand off to infinity. So this is good, a good example to keep in mind. Now, the motivation for studying inverse mean curvature flow historically actually came from general relativity, but I'll actually give some other kind of physical motivations / application a little bit later in the talk. For now, I want to talk a little bit more about the dynamics of this equation. And I want to start with just talking about like dynamics of geometric flows in general. So one broad question in not only geometric flows, but just evolution equations in general is questions about singularities. So for some choices of initial surface, the flow surfaces of a geometric flow might approach a limiting shape that the flow cannot be continued from in time. And to demonstrate what I mean, I included a picture not of inverse mean curvature flow, but of mean curvature flow. If you take a dumbbell shape in R3 and you evolve it by mean curvature flow, it's possible that the neck of the dumbbell shrinks faster than the rest of the surface, and it causes the neck of the dumbbell to pinch off at the axis of rotation, resulting in what's called the neck pinch. And this is an example of a singularity in mean curvature flow. So the definition of a singularity is pretty simple. If you have any geometric flow, you would say that it has a singularity at some time t if there does not exist a time greater than t, and a solution defined over the corresponding larger time interval, which restricts to the original solution over 0t. And a different way of saying this is just that a solution has a singularity at time t if it cannot be continued further in time. The issue of trying to continue a solution like this further in time is that any solution defined over a larger time interval would include this set right here, which does not have well-defined mean curvature and is not a surface in any reasonable way. So we'll talk a little bit more about like necessary and sufficient conditions for singularities in a little bit, but what does everyone think so far?
How do you know that the solutions are unique?
Okay, so yeah, they're unique up to gauge choice. So if you so really what you're interested in is a one parameter family of surfaces, but there will be many ways of parametrizing these surfaces through time. And that means that like if you're just looking for a one parameter family of emergence whose images are the flow surfaces you're actually interested in, there's not a unique choice. But if you impose the gauge condition, which like I'm implicitly doing here, in the equation for inverse mean curvature flow, the uniqueness just follows from the fact that this PDE is parabolic. So like parabolic problems will always have unique solutions in short time, basically. So it's geometrically unique. The flow surfaces are unique, but the ways of describing them are not. Okay. So I want to talk a little bit about singularities specifically for inverse mean curvature flow, because I think there's a lot of interesting stuff going on here that maybe has been overlooked before. So the only example coming into this dissertation of a singularity in the inverse mean curvature flow was that of a thin torus. So if you take a torus in R3 where the radius of like this tube is small enough, the torus will have positive mean curvature everywhere, meaning that you can run inverse mean curvature flow from this thing. And of course, the torus will expand outward, which will make like this little donut hole here smaller. As this hole is becoming smaller, the curvature associated with like rotation in this direction is getting driven further down. It's negative and it's getting driven down to minus infinity. So since the mean curvature is the sum of that curvature and another curvature, inevitably mean curvature will reach 0 along this inner ring so that the flow speed will blow up. And you can't continue the flow any further beyond blow up in the flow speed. So this thing expands, mean curvature hits 0 along the part of the surface that's closest to the axis of rotation in the middle right here, and that causes a finite time singularity. So this is a known example of singularity formation in inverse mean curvature flow. But one question that I think is interesting that has been maybe neglected is, does this torus pinch down at its axis of rotation at the singular time? In other words, mean curvature will eventually go to 0 by like a sort of heuristic argument, but at the singular time, does the torus actually reach the central axis of rotation, or does mean curvature hit 0 before it has a chance to do so? This might not seem like, so you might ask like, well, why do we care? So from the standpoint of PDE analysis, if you had no pinching, the result would be pretty surprising, because what it would mean is that the total curvature, again, that's like the square root of the sum of the squares of both principal curvatures, the total curvature would stay bounded in L infinity norm up to the singular time. And this would also imply the existence of some sort of limit surface as you approach the singular time. So if you know anything about like evolution equations in general, the second fundamental form is sort of like a nonlinear version of the Hessian. And typically when you're studying parabolic PDE, if you have an L infinity control on the Hessian, that's a sufficient condition for continuing further in time. You know, when I started this project, it looked possible to me that like you could have an L infinity control on the second fundamental form, yet not have continuation further in time because mean curvature is going to 0. And that's exactly what I found. So the first result that I'd like to highlight is I showed that no pinching occurs for the thin torus. And I actually proved something more general. If you take any torus which is rotationally symmetric with respect to some axis, you get the same thing. You get boundedness of the total curvature up to the singular time, and hence a limit surface. So this is the first thing. If you have any rotationally symmetric embedded torus in R3, and you take this solution to inverse mean curvature flow, the second fundamental form stays bounded up to the singular time. And this allows you to extract a limit surface. Now, I'm being a little hand-waving when I say what a limit surface means. Really, you want some sort of limit immersion that the immersions approach an appropriate topology. You might need to pre-compose with surface diffeomorphisms first in order to obtain this limit immersion, but some sort of limit immersion modulo subsequences and surface diffeomorphisms should exist. And this is actually the first instance that I know of a solution to an extrinsic flow and Rn+1 exhibiting this sort of behavior. Limit surfaces are studied in other geometric flows, but typically you need to blow the surface up to find them, like scale the surface up in time in order to find them. And here you have a limit surface without any sort of rescaling. So that's the first thing that I'd like to highlight, no pinching in the torus. And I also will say that it suggests like some more general behavior that I think is interesting. That's going on here. Chat question. Is taking a subsequence necessary? Well, actually, so to Gavin's question, my suspicion is that not only is taking a subsequence unnecessary, but that you don't need to compose with surface diffeomorphisms. I think there's a way of showing that like in the chart that you have, everything stays in immersion. But I had something that was really close to a proof of that, but not quite. So the reason that I have this whole subsequence business is because I just cited a result from another paper, basically, about like a compactness theorem for surfaces. Okay, yeah, anything else about this result? Okay, so that's what I have to say about singularities for now. I'll go more into the proof of this result. It's a very geometric proof later, but now I want to talk about what happens when you have no singularities. So of course, there are certain choices of flow surfaces where you have no singularities, in which case that you would say the maximal time of the solution is plus infinity, so it exists forever. So does this break down for thicker tori? So when I say thin torus, I just mean it needs to have positive mean curvature everywhere. If it was thick, then it wouldn't necessarily have positive mean curvature everywhere, and you couldn't even start mean curvature or inverse mean curvature flow from it, because mean curvature needs to be signed. So thin, I just mean positive mean curvature, basically. Okay, so next I wanted to speak a little bit about dynamical stability in geometric flows. Like I said, certain choices of N naught, the corresponding solution, could exist forever. And a very natural question to ask if the solution does exist forever is, is there some sort of asymptotic limit of the flow surfaces at large times? That is, do they approach a limit surface like a round sphere as t goes to plus infinity? So like, you know, you could have, I mean, I'm not really sure which geometric flow this is, but you could have a geometric flow that takes something which is not a sphere and then just gradually makes it into a sphere, where again, the convergence is understood in like convergence of immersions. So if n naught is some perturbation of the round sphere, you can view this as a dynamical stability problem for an equilibrium solution of a PDE. In other words, the way that you can think about this question of does NT approach a fixed limit surface is, we know that for geometric flows like the inverse mean curvature flow, a sphere retains its shape as it evolves, right? This is typical for geometric flows, that if you take something special like a round sphere, it will remain round under the flow. And this makes you ask the question, if I somehow deform or perturb a round sphere a little bit at the initial time, will the corresponding solution in that case exist forever? And will it converge back to a round sphere at large times? Okay, so round sphere retains its shape. There's this natural question of, if I deform it a little bit, will the evolving surface converge back to a round sphere as t goes to plus infinity? And this is a dynamical stability problem for a PDE. So the first major stability result for the round sphere in inverse mean curvature flow comes from work by Klaus Gerhardt in 1990. What he was able to show is that if you have an initial surface which is star-shaped, and there's more than one definition of star-shaped in geometry and topology. The definition that I'm using is, you would say something is star-shaped if the normal component of the embedding vector is everywhere positive. So like, I drew a surface here that looks like a star, and that you can like take an embedding vector with respect to the origin. And if the normal component of the embedding vector, like taken with the normal of the surface at each point, is everywhere positive like it is here, you would say the surface is star-shaped. Gerhardt was able to show that if a surface is star-shaped and has positive mean curvature, then the following are true for its inverse mean curvature flow. First, its inverse mean curvature flow exists forever. Second, its inverse mean curvature flow stays star-shaped. And third, the rescaled flow surfaces approach a round sphere in the sense of C2 convergence of the rescaled immersions as time goes to plus infinity. So he was able to show that like star-shaped perturbations of the round sphere, which are like a very general class, it's a very weak assumption on a surface, converge back to a sphere under inverse mean curvature flow. And this is actually quite surprising because the PDE that inverse mean curvature flow defines is fully nonlinear. You don't need to know a whole lot about PDE to think that like fully nonlinear PDE are going to be difficult to say anything about. Nevertheless, he was able to show that like under this very general family of perturbations, you have long time existence and you have convergence back to a sphere, which is pretty surprising for equations that are as nonlinear as these. So for this reason, I became interested in what like non-star-shaped perturbations is the round sphere stable under in inverse mean curvature flow. And natural perturbations to consider here are surfaces of rotation, as in like dumbbell shapes in Rn+1. So basically consider a perturbation of a sphere that maintains rotational symmetry with respect to some axis. Perturbations like these have been studied like pretty extensively under other geometric flows like mean curvature flow, wherein you can get singularities like a neck pinch. I was interested in like what happens to dumbbells under the inverse mean curvature flow when the flow expands outward? Do you get something bad happening like a saddle point formation, or does the mean curvature stay bounded away from zero as you allow this thing to expand? That was the motivating question for this project. And before I go any further, it turns out that like saying anything about just any rotationally symmetric perturbation in general is difficult, right? Like rotationally symmetric is a super weak assumption on a surface to be able to say anything about with analysis. So what I was able to do is I was able to say something about dynamical stability when you have an additional assumption on the rotationally symmetric surface. So for any surface like this, one of the principal curvatures will always correspond to rotation about the axis, right? So like rotation in this direction. That principal curvature will be a constant if the surface is a round sphere. So basically, I was able to figure out a dynamical stability result that depended on how much this principal curvature right here deviated from being a constant. And this is the second theorem that I'm going to talk about. So I showed that if you have any rotationally symmetric surface that satisfies an additional condition on the curvature of rotation, which I'm calling P, you can get the same sort of results as you do for star-shaped surfaces. So if the maximum value of the curvature of rotation divided by the minimum value of the curvature rotation does not exceed n to the power of n over 2 to the n minus 1, then you get all the same sort of results that Gerhardt found for star-shaped perturbations. And I know this upper bound on this ratio here looks a little bit artificial, but that's just kind of like what happens when you do analysis sometimes. Random looking things pop out. But if you want to just like do a little sanity check, if n were equal to 2, this number would be 2. So you can say that like any rotationally symmetric surface where this ratio is smaller than 2 in R3, it will converge back to a sphere under inverse mean curvature flow. Also, if you're like still perplexed by this condition right here, just suffice it to say that what it's indirectly doing is it's controlling the shape of the necks. You might imagine that it's more difficult to say something about the evolution if the neck is very thin relative to the rest of the surface versus if the neck is a little bit thicker. So what this curvature condition indirectly does is it requires a certain minimal thickness to the necks. You can say something in that case. And I just explicitly like constructed examples of non-star shaped surfaces that satisfy this condition here. So these are some new dynamical stability results in inverse mean curvature flow. And that's the second thing that I'll be presenting on. Questions about this? Okay. Now, lastly, I'm going to present some motivation for studying these kinds of problems. I know that it goes against conventional wisdom. Oh, 1 second. Yeah, the Brian Knight's question. I think it still is true if the necks are thin. There's actually good evidence that like I found that it still will be true if the necks are thin, but I don't have a formal proof of it yet. It's something that I might work on next, is showing that you can drop the curvature condition and all of that stuff will still be true. But I don't have the formal proof yet. So lastly, I wanted to present a little bit on like physical motivation for inverse mean curvature flow. Now, I know it might seem a little odd to do motivation after you've talked about everything else, because then it's not as much motivation. But I didn't learn about this till after I did all the other stuff. which is interesting in its own right that I found out later. This I actually found out about the connection from Joel, who needed to leave because he had a committee of some sort to sit on. But there's this interesting connection between inverse mean curvature flow and physical soap films. So if you've ever taken a loop of wire, closed loop of wire, and dipped it in like a vat of soapy water, you'll know that you pull the wire out and the soap film clings to the loop, right? And there's an ancient, well, I don't know, maybe not ancient, but there's an old question in geometry about like, why does this surface have the shape that it does? So the way that you mathematically model a soap film is the loop is modeled by a closed embedded curve in R3. So let's just assume it's a curve with no self-intersections. And the film is modeled by an area minimizing surface whose boundary is this closed embedded curve. Oops. So area minimizing in the sense of all surfaces which attach to this curve, the surface that or the shape that the soap film takes has less area than all of those other options, right? So soap films like to minimize area. They like to minimize the amount of film that they're using to cling on to a surface. And something that I will highlight is that a necessary condition for a surface to be an area minimizer is for its mean curvature to vanish everywhere. So remember that mean curvature is the sum of the two principal curvatures. So what this is telling you is that in the model for a soap film, one principal curvature is positive and the other is negative, so that their sum cancels out at every point and every point looks like a saddle. This is what accounts for the shape of this soap film right here. One principal curvature is positive, like in this direction, and the other is negative at every point. You can show that if mean curvature did not vanish at every point, then you could make the area of the surface smaller and it would no longer be an area minimizer. So I should also mention that the picture that I included here is not especially impressive, but if you're interested in the math of soap films, then Google soap films and there's just absolutely beautiful pictures. I just included this one to get the point across. So what does inverse mean curvature flow have to do with this? So there's a major problem. Well, I don't know how major it is. You would need to ask like people who study like physical soap films for their opinion on how major it is. But there's sort of a problem with these models for soap films, which is that we know in general it's possible for an area minimizing surface to self-intersect. And physical soap films cannot self-intersect. Not self-intersecting is equivalent to not being embedded. So for a curve like this, you could have a minimal surface that intersects itself at like these points right here. So this is a very puzzling aspect of minimal surface models for soap films. And there's been some work done on like, in what shapes can you form the curve to guarantee that the minimizer is embedded? So one example of this work is by William Meeks and S.T. Yao. So they studied the problem of which choices of boundary curve give rise to embedded minimizers. And they considered boundary curves in R3, which were confined to a mean convex surface. So they said, like, what if we require that our gamma is sitting on a mean convex surface? What can you say about its minimal surfaces in that case? And what they were able to show is that in that case, there will always exist an embedded minimal surface that gets enclosed by the surface gamma is sitting on. So, you know, in other words, you have a surface in R3, you have a curve that lies on the surface, and you have an embedded minimal surface that goes inside of and the region enclosed by N naught. The thing about the result is that it does not rule out the possibility that there are minimal surfaces which lie outside of N naught. So it's possible that there exists some non-embedded minimal surface that goes outside of the surface N naught. is not enclosed by n naught, and this might be allowed to self-intersect. So basically what this work that I've been talking about for the last half hour or whatever accomplishes is it allows you to actually rule out the existence of these possibly non-embedded minimal surfaces, which leave n naught for certain choices of n naught. Maybe I'm getting too bogged down in the technical details, but basically you can show that if a curve lies on a surface which gives rise to a global embedded solution of inverse mean curvature flow, so a solution that exists forever and never intersects itself, there's only going to be one minimal surface for the curve gamma, and it will need to be enclosed by n naught, and it'll need to be embedded. So there can't be any minimizers outside of n naught. All right, so that was a lot, but questions about this? Oh, sorry, mean convex just means positive mean curvature. Yeah, so they studied curves that lied on positive mean curvature surface, and they said we can always find a nice minimal surface that gets enclosed by the positive mean curvature surface, but we can't say whether or not there are ones that don't get enclosed by the minimal surface. And basically this result says that in some cases you can rule this out. Okay, anything else? All right. Yeah, so my time frame was like about 75 minutes. Like I was thinking with maybe like 5 minutes of questions at the end. I don't know if I'll reach that that objective, but I could also like just kind of say less about the proofs. We'll see. So let's talk about the first theorem that I proved. No, it's a fixed boundary curve, Simon. I'm just saying, like, you have a fixed boundary curve and you want to know something about surfaces that attach to that fixed boundary curve. Okay, so for the first theorem that I mentioned, remember that we were interested in tori that are symmetric with respect to an axis, and it should be R3 here, not Rn plus 1. But tori which are symmetric with respect to an axis in R3. So let y min of t be the minimal distance of the flow surface to this axis. Our goal is to show that y min of t does not go down to 0 as one approaches the singular time, because in turn this will tell you that the maximum value of the total curvature stays uniformly bounded up to the singular time. So the key to the proof is the Gauss-Bonnet theorem. And I'll say what that is in a few slides, but what we ultimately showed, or what I ultimately showed, was this, and that in turn implied this. So basically the way that I proved it was with an argument by contradiction that involved rescaling. So when I say contradiction, assume that y min of t goes to 0, and then rescale each of the flow surfaces by 1 over y min of t. So these scale factors are going to plus infinity. And what you know if these scale factors, so I just mean like blow the surface up. If you blow the surface up by 1 over y min of t and assume that y min of t approaches 0, then what you know from that is that mean curvature is going to go to 0 everywhere on the blown up surfaces as one approaches the singular time. So you're making the surfaces bigger and bigger with time, and that makes the mean curvature smaller and smaller with time because mean curvature scales like 1 over the scale factor. So this tells you that mean curvature of the blown up surfaces is going to 0 everywhere along the surface, and this actually suggests a certain candidate limit for a piece of the flow surface. So the idea here is to show that the part of the blown up flow surfaces which are close to the axis of rotation converge to a catenoid, which is a minimal surface that's parameterized by this graph over all of R. So here's kind of all of what I'm trying to say summarized. The argument that you want to make is assume y min of t goes to 0, blow the surfaces up so that they approach a limit surface, figure out what the limit surface must be, and then rule out that limit surface as a candidate limit. And that'll rule out this possibility. So the key to showing this is the Gauss-Bonnet theorem. So for those of you who aren't familiar, the Gauss-Bonnet theorem relates the integral of the Gauss curvature, which is the product of the two principal curvatures over a surface with boundary, to a boundary integral and the Euler characteristic of the surface. Without defining what any of these things are, the point is that you can figure out something about the integral of the Gauss curvature that depends only on topology of the surface and a boundary integral. So what I used Gauss-Bonnet for was I was able to say that, like, on the unscaled surfaces, part of them need to satisfy the following estimate. The integral of their Gauss curvature must be smaller than 4 pi times 1 minus epsilon. So ST is like a part of the surface that goes between two parallel planes. And this is like a cross section of the evolving flow surface. So S of t is the part of NT that lies between two parallel planes and is close to the axis of rotation. I was able to show that this part of the surface, the Gauss curvature remains uniformly bounded away from 4 pi. And this is basically how you rule out blowup for the catenoid. The way that you rule out convergence to the catenoid. So this estimate is scale invariant in R3. For n is equal to 2, area scales like scale factor squared. Gauss curvature scales like 1 over scale factor squared. So the energy estimate of the blown up S of t's satisfies the same, or the energy estimate passes to the blown up S of t's is my point. So the generating graph for the blown up surfaces will need to approach the generating graph for a catenoid in C2 loc of R. And you can derive a contradiction from this because a catenoid always has Gauss curvature 4 pi. So since I know I can kind of condense what I'm saying a little bit, the point is you look at the flow surfaces under a microscope. You say they should look like a catenoid, and then you say they can't converge to a catenoid because their Gauss curvature is too small. So that's the big picture. I don't know, maybe I should stop again and just ask if anybody has any questions.
If they don't converge, if this point doesn't converge to 0, then do you have any sort of formula for kind of how close it's getting to 0 based on maybe the curvature of the surface to begin with or something?
So this argument is not constructive, I guess. This argument only tells you that the limit of the distance is not 0. It doesn't tell you what it actually is, but it's not 0. I'm sure whatever it is, it's going to depend on the initial surface in some way at least. So all you can really say, I guess, is that it's not 0. Whoops, sorry. Okay. So from this contradiction, you have a bound on the curvature of rotation. It in turn implies a bound gives a bound on the total curvature. The existence of a limit immersion modulo surface diffeomorphisms then follows from a compactness theorem due to Joel Langer. And something that I can talk about at the end, for those of you who are interested, is that there's evidence that this generalizes to any singularity in R3. So I can say more about that later, but the point is that you have no pinching in the torus if it's rotationally symmetric. Okay. So I wanted to say a little bit about the rotationally symmetric stability proof. Remember, we're considering surfaces of rotation that satisfy this condition. And we want to show three things. We want to show that the inverse mean curvature flow exists for all time, stays a cylindrical graph, and converges to a round sphere at large times. So we'll address items 2 and 3 first because they're easier to answer. So item 2 is just saying that like a surface of rotation is generated by revolving a curve about the y-axis, right? Or the x-axis, right? What we want is that the generating curve is actually a graph rather than, not a graph like this. And you can verify that if you have a mean convex sphere, rotationally symmetric sphere, the generating curve needs to be a graph, just as a consequence of the fact that you need mean curvature to be positive initially. And then you can verify that if the initial generating curve is a sphere, the generating curve for the flow surfaces is a graph, the generating curve for the flow surfaces remains a graph. So the generating curve of N0 and NT are a graph. This just comes from like figuring out consequences of positive mean curvature. And what this is telling you is that NT does not intersect itself as long as the flow exists, because graphs cannot intersect themselves. So that's how you show that you are like nice and embedded as time progresses. For the third item, I showed that any embedded solution. So the third item uses another result from an earlier paper that unfortunately I can only cite here. I can't actually explain. But what I showed in another paper was that any embedded solution of inverse mean curvature flow that exists for all times becomes star-shaped after an explicit time. So what this tells you is that for dynamical stability problems in the inverse mean curvature flow, all you need to show is T max equals plus infinity and no self-intersections. If you have those two things, the surface will eventually become star-shaped. And we know from Gerhardt's convergence theorem that star-shaped things converge to spheres. So to summarize, 1 is the hard thing to prove, 2 is pretty easy to prove, and 3 will follow from 1 and 2. So the hard thing is 1. Now, how do you show that there are no singularities in rotationally symmetric inverse mean curvature flow? Well, the important characterization due to Smockchick and Hwiskin and Neilmannen is that any singularity is characterized by mean curvature going to 0 somewhere along the surface. So basically you can guarantee that if mean curvature stays away from 0, you have no finite time singularities in the flow. 0 mean curvature is the enemy here. So we need to show that mean curvature does not go to 0 in finite time, or equivalently, we need to show that the flow speed does not blow up in finite time. You can show that all the other important geometric quantities that you need for a long time existence are controlled as long as this is controlled. So the objective in this project, like the hard objective, is to show that flow speed does not blow up in finite time. And this just is where the PDE analysis comes in. You need to do some hardcore PDE analysis to show this. And in order to successfully carry this out, you need to break the flow surface up into different regions. So I needed to define separate regions of a rotationally symmetric surface myself to go any further. I said that if you have something that looks like this, the caps of the surface are the blue regions. I called this the left cap and this the right cap. And I called their complement in between the bridge. Basically, what we want to do is we want to be able to analyze the bridge region of the evolving surface NT and the cap region of the evolving surface NT separately. So you can think about the union of all caps through all times and the union of all bridges through all times as domains in space-time, right? Because like you have spatial variable, which corresponds to a fixed time, and a time variable too. So you can think of the union of all caps through time and the union of all bridges through time as giving you domains in space-time. So the way that we're going to separately analyze these regions is with the parabolic maximum principle. So once again, I keep saying that like people who have done any PDE analysis will probably be familiar with parabolic maximum principles. But basically a parabolic maximum principle allows you to control the size of certain geometric quantities that you associate with a geometric flow. If you have some function that's defined over space-time in the standard parabolic maximum principle, basically you can verify that if it satisfies a certain differential inequality, then its supremum is not growing in time. If I don't know how many of you have ever seen the Laplacian. This is a Laplacian-like operator known as the Laplace-Beltrami. This is the time derivative. And this is the gradient. But if you have a function that satisfies a differential inequality of this form, what you can show with just rules of calculus is that this quantity cannot exceed its initial supremum, right? So like you want to make sure that f does not get too big, and you can do that by showing that it satisfies a differential inequality of this form. Okay, so parabolic maximum principles are very useful because this is the game, right? You're trying to make sure quantities don't get too big as the flow surface evolves. And what we'd like to do is we'd like to apply parabolic maximum principles separately over the union of all bridges, the union of all left caps, and the union of all right caps, which will give us an indirect way of controlling flow speed. Now, I actually needed to introduce a little bit of a modification of the parabolic maximum principle for this to make sense, but to suffice it to say that at the end, you can get the parabolic maximum principle to hold just over the domain L, just over the caps C plus and C minus. Yeah, so I don't know if I want to get too much into detail because I already got maybe too much into detail already. I guess maybe I'll just, rather than go through all of this like thoroughly, just kind of give you a brief overview. The point is you want to analyze the cap regions and the region in between the caps separately because different quantities are doing good things over different regions. So you basically know that, I don't have any pictures of, oh yeah. You basically know that for an admissible surface and not, that the slope of this like dumbbell shape is uniformly small. And you know over the caps C plus and C minus that the flow surface has a certain star shape to it, but just over these regions. So I think I'm getting too weighed down in everything specifically. Like, so I guess the point of this is just that there's like different things that you can exploit here versus here. And altogether it leads to a bound on the flow speed. So yeah, I didn't rehearse this part prior if you didn't notice, but I think I'm getting too weighed down. So I'm just going to say, like you just play with maximum principles until the problem is solved. So probably you don't have questions about specifics, but do you have questions about like general overview? Okay, so lastly, I want to say a little something about the third theorem that I presented, which is about area minimizers. So again, recall that we're considering curves that lie on mean convex surfaces. And we want to know what happens when that surface admits a global embedded solution to inverse mean curvature flow. So we'd like to show that the area minimizer for gamma is always embedded. And we know that there is an embedded area minimizer for gamma, but there might also be non-embedded ones. So we want to rule out the existence of non-embedded ones. And basically the way that you can do this is with a comparison principle. So comparison principles are used frequently in geometry. Basically the way that you use a comparison principle here is, let's say that you had two surfaces and one got enclosed by the other, but they touched at a point. At the point where the two surfaces touch, you know that the mean curvature of the inside surface needs to be bigger than the mean curvature of the outside surface. So I actually include a picture on the next slide. Let's say you have this surface that I have in like light gray and this surface that I have in blue. If the blue surface gets enclosed by the gray surface, but they touch at a point, you know that wherever they touched, the blue surface needs to have greater mean curvature than the gray surface because it's curving more in every direction than the gray surface is. So what you can do with a comparison principle is you can use inverse mean curvature flow to give you a nice foliation of the exterior region of N naught. And then it allows you to locate a surface that will touch any surface with boundary curve gamma. Okay, so given a surface attached to gamma, any surface which leaves E naught here will need to touch a mean convex surface just at one point. And via comparison principles, it allows you to conclude that any surface which leaves gamma must have positive mean curvature at one point. So the point that I'm trying to make is that using a comparison principle and the nice foliation properties that you have due to inverse mean curvature flow, you can always guarantee any solution that leaves the region enclosed by this surface here. Any surface that leaves the region enclosed by N naught here will need to have positive mean curvature at one point. So the take home is that, the take home is that any minimal surface has vanishing mean curvature everywhere, and any surface that does not get enclosed by N naught needs to have positive curvature somewhere. So this allows you to rule out minimal surfaces that go outside of a certain region and establish embeddedness for the one minimizer that you know you have. So yeah, I feel like the proofs themselves got a little bit muddled, but does anyone have any quick questions about comparison principles and all this sort of thing? Okay, well, yeah, that's actually all I had to say. So I guess I went kind of quick through those proofs. I don't think I needed to go through them as quickly as I did, but we're at the end anyway, so I guess I'll just stop there in that case. All right, yeah, does anyone have any questions about anything at all?
You said you expect the, like for non-torus surfaces in R3 that they don't pinch. So is the statement that like the PDE can't go on for all time, but even when it stops, it still is a nice smooth manifold that it never actually like geometrically.
C1. Yeah, I guess the point is that like my thinking is that for any surface in R3, even if you have finite time singularities, you still extract a limit surface without rescaling. So like that would follow if the second fundamental form stayed bounded. My reason for thinking this is that like kind of the procedure that I described earlier was just like it seems like the procedure I described can generalize, but I don't know how to do it yet.
Mm-hmm.
I have a question that might be kind of strange for the topic, but you have a singularity that forms. Is there any notion of weak solution for these types of problems that might allow you to continue past the singularity?
Yes. Yeah. So this is the part that I wasn't able to talk about that I alluded to at the beginning of the talk. So there's a paper by Gerhard Huisken and Tom Eelmannen where they develop a theory of weak solutions to the inverse mean curvature flow, and they take a level set approach. I don't know if, so if you've ever seen like level set solutions to mean curvature flow, you can talk about level set solutions to inverse mean curvature flow, and then you can use that to define a notion of like a weak solution as a solution to an elliptic problem. Yes, so there is a way for sure to flow past singularities. And I prove a few things about weak solutions in the dissertation too.
Okay, thanks.
What are the gauge freedom that when we quotient out the inverse mean curvature flow has a unique solution? What are the gauge freedoms? Rigid motions?
Tangential diffeomorphisms. So really what you're interested in when you're studying inverse mean curvature flow is a one parameter family of immersions where the normal component of the velocity vector is 1/h. So that means that if you take any solution and then any like sequence of any one parameter family of tangential diffeomorphisms, the resulting immersions that you get by pre-composing will still like give you the same flow surfaces.
Okay,
so
I see.
I guess
it's like as an embedded set into Rn, the manifold itself shouldn't change, but we can rename the different points on the manifold.
Exactly.
Yeah. Okay, got it.
So I was going to go back to that, but that's it.
So I also wanted to ask about these stability results, because these are like serious nonlinear stability results, right?
Mm-hmm. Mm-hmm.
Are there other results? Do you gain anything by linearizing, or is the problem just too horribly nonlinear to do anything with that? Can you get linear stability results, or does that just not make sense?
Yeah, I guess I'm not really sure what like linear stability would mean for a geometric flow. I mean, I didn't look into linearizing at all. I just worked with the actual PDE.
Sure.
I mean, I'll say as far as the dynamical stability results go, I mean, the main thing is just that there's like lots of nice geometric things happening that are just sort of like hidden behind like really complicated reaction diffusion equations. Like the thing that kind of got me going on this project was, so what I was able to figure out is that the principal curvature of rotation satisfies a PDE that has like, you know, cubic nonlinearities in the reaction term. But if you actually look at what's happening at critical points of P, that reaction term starts looking very nice. So there is hope of controlling it via maximum principles because of the fact that at critical points of that curvature, the surface is actually umbilic. So there's lots of nice geometric things going on that sort of reduce the PDE and make them look more more linear at the critical points, which is what you really need.
So what you're suggesting is that sort of throwing ordinary PDE techniques at it is probably not the best idea because there's so much extra geometry going around that informs.
Well,
PDE.
I mean, so it depends. Yeah, I mean, it depends whether or not you consider. I mean, I would say maximum principles are pretty normal PDE techniques.
Oh, absolutely.
The only issue with you know, like using a maximum principle here again is like, you know, these surfaces close up, so you get these extra caps that you need that require you to break the surface up into separate regions. But there's something interesting going on with the maximum principles, even though initially the evolution equations themselves don't look like there's any hope, you know, of applying maximum principles.
Okay.
So yeah, there's something geometric that's like hiding beneath everything, I guess, is my point. And I think that's the main reason that I think you won't get singularities in the general case. I don't have a proof of it yet, but it just seems like something deeper is going on.
Sure, thanks.
Anyone else? Okay. Yeah, so probably I should have rehearsed the second half a little bit more. I think I went more in the weeds than I wanted to, but it happens. Great. So
Right, let's
Yes,
think one more time. Sorry, I forgot to say it right after your talk, you know, thank you and ask for questions. I forgot my host role pretty quickly.
Okay. Yeah. All right. Sweet. So, like I said, third and U at 5 for those of you who are interested. Of course, it'll be outdoors. Be nice if you're vaccinated too. And I'd love to see you there. Yeah, otherwise, thank you all for coming. And I think I am going to end the meeting now unless anybody has anything else they want to say. Okay, well, yeah, peace.